I'm very glad that Professor Frank Lechermann from the Ruhr University, Bochum, agreed to give this tutorial today on dynamical mean field theory. And then he'll be giving a talk later in the meeting, I think tomorrow, on using these kinds of ideas to think about the nickelate superconductors. So maybe I'll try.
Yes, thank you. Yeah, thanks a lot, Arun, and all the other organizers for having me here. It's really a great pleasure to be at this place. It's a really beautiful place. So it's my first time in India, and it's really very nice. Also, the conference is very nice, so I like really the style here, and I'm also impressed by the students and by the poster sessions and by the talks. So it's really impressive. So against this background, so this is really a tutorial. So Arun was asking me to give a tutorial on DMFT, and I didn't really know the scope and the background of all the listeners, so I made it pretty simple, I think, from my perspective. There will be some equations at some later point. So it'll be like 2-3 slides, which will be a little bit heavy and maybe for some of you a bit new, but I think most of it, what you will see, will be more or less basic, I hope, and things that you might have seen in your course lectures, and maybe just reminding you, and maybe also seeing that there are some very basic principles that you have learned maybe deep in some early lectures on solid state physics, which still come up again when one has to think about DMFT and what are the whereabouts of DMFT. So it's always good to have these basics ready, and so maybe it's not a bad idea to start from there. So let's start on this, and just be free to ask questions all the time. Stop me at any time you want to, and we want to discuss a little bit. That's of course very important to get the physics. So this is a bit the outline of this presentation. So again, I will give you a very brief account of what is about condensed matter electrons, band theory and beyond, so to say. And then we will talk a little bit what we have to think about when we want to treat strongly correlated electrons, because as you, of course, have already realized, that is what is DMFT about. And especially that we've selected a good vantage point, meaning what kind of theoretical strategy we are using to address strongly correlated electrons. We will find out that Green's functions are a good way to do that, especially in the strongly correlated regime. And then we will go forward and try to find the good, so to say, object that can describe strongly correlated electrons in a regime where really interactions are, well, strong. And then we go to the basic principles of dynamic and field theory. We'll see that dynamic field theory is some kind of an optimized way to treat that problem from a given perspective. And that's more or less it, no? And then we have maybe an outlook, so that it depends a bit on time. Of course, you know that there's this combination of DFT with of DMFT with DFT, so that it can bring this to a realistic materials world. It's of course highly appreciated to have such a method at hand. So what we will see on time, how we will doing, and how much of this we can address. But just feel free to ask questions, and if we cannot cover all of this, I'm of course very happy to discuss this afterwards or any time you like to. Okay, so let's just jump into the field. Again, I try to start simple. So, and when you want to start simple on physics, on quantum physics and condensed matter, it's best to start maybe with the Heisenberg principle that gives you some idea of itinerancy. So sometimes if you ask students about what is about quantum physics in condensed matter, they think hard and they come up with superconductivity or quantum criticality, some very fancy things. But you don't have to go that far to look for quantum principles, because a very chemical bond that puts all of us together in some respect, not only the solid state, is of course already a very quantum aspect and a quantum mechanism. So without quantum physics, you would not have anything bonding in nature, which of course would be quite a hassle then to the bond. So the basic idea is that you have here isolated atoms, let's say hydrogen atoms, that do not bond. And of course, they don't want to bond classically. Why should they? Because they're all charge neutral. So there's no reason classically that they will exchange electrons. No, there's no reason, because they're all happy by themselves classically. But of course, you realize that if they would find such a bonding structure, then there would be some other restrictions on their positional variance and their momentum variance, because the positional variance would be much higher here than there, meaning the momentum variance would be much smaller here. And this would, in the back of an envelope calculations, which you all have maybe seen before, you can easily from that get that the kinetic energy is then lowered in this bonding scenario. That's just the reason why electrons like to hop from one atom to another, and also in the solid then become itinerant and like to hop from one place to another. And it's of course a very important principle that also is very much governing also the strongly correlated regime that we're tackling later. So if you continue on this, of course you start just from individual atoms. You can have a certain scenario of PZ bonding, and then you know what happens in a solid. Well, we crank up a solid by going to a chain of atoms. So we have two atoms, and they form a bonding and anti-bonding orbitals, and so on and so forth. If we add more and more atoms, you see that we will gather more or less a phase of adjusting these different PZ orbitals along a chain, and this phase, of course, transfers then to your K vector that governs the state and also governs, as you know, the dispersion of the energy. So the most in this PZ-like sigma or this PZ-like pi bonding, the most attractable state is the Marioch bonding state, and this is the most undebonding state, if you like. It depends, of course, on the orbitals you have. If you would have px orbital, then the dispersion would be a bit different, but that's, of course, all what you know already. So then, if we really go then to the more or less continuous like K vectors, we enter this band theory. Yeah? So we have a band of states, so each point on this curve represents a certain quantum state of your solid, like a huge molecule, so to say. And so the minimum as in our PZ orbital scenario is at the gamma point at 0, and it goes up to this most alternating orbital scenario at the Brion zone boundary, and we have the Fermi energy where we have to fill up electrons up to a certain level. Yeah. Dispersion and this minimal tight binding picture is of cosine kind, and what we mean by this in the end that we have a Bloch state that continues on the lattice with some periodicity. So it's not the full periodicity of the symmetry group of the lattice. It's just because it's a function on this lattice, but it has a certain phase vector governing if you go from side to side, and it more or less condenses in this Bloch form here written in a tight binding manner for having a basis of quasi-localized orbitals that pile up to your lattice state. And then you fill up in K-space these different rooms for the various electrons, and then you end up at a Fermi surface if you have a metal. That is a very basic scenario for non-interacting electrons, which of course you all know already. Now, of course, you know that this is not the full story, although some people try to convey this in already lectures that this is the full story. It's not, because of course electrons are interacting, and we have completely ignored that fact in our treatment so far. So if you want to deal with interacting electrons, then we have to obey the Pauli principle that tells us that we cannot put electrons in the same quantum state. And that immediately transfers to the statement that we have to have a fully antisymmetric wave functions for our electrons, which in the simplest case is a Slater determinant. But again, a Slater determinant is just a very simple object. That's also sometimes for students, when I give lectures, very hard to understand, because Slater determinants usually come at the very end of the lectures sometimes, and they think, wow, that's a very fancy thing, Slater determinant. That's the most heavy thing that I've learned about. But of course, you know that's just the simplest thing you can get for interacting electrons, because it's just a product wave functions which is antisymmetrized. So there's no correlation in that. That's a very simple object in the perspective of correlated electrons. But still, it's a good starting point, because we know that in quantum physics, we always can use in theory the principle that we can have a select basis state, which we can select at our will, and then expand the interacting problem within this basis. Yeah? So Slater determinants are a good basis for this, obviously. So that is the basic principle. If we go now to interacting systems, let's say again a H2-like problem, but now on a chain and with having interactions in mind. So then, of course, we have to be a bit careful. So we more or less neglect this hopping first of all altogether, and we crank up some basis states, which are now our Slater determinants, which would be these 4 neutral configurations, yeah, of spin up here, spin up there, and continuing like this. You can all see that. That is this some kind of Heitler-London picture of the molecular bonding. And then you would also have to put into the game these ionic configurations where there are 2 electrons on each side, of course, obeying the Pauli principle. And this is, so to say, your basis state where you would like to diagonalize a problem. And if you do that, maybe, of course, you all know that also already, that the ground state in this manifold of states that you use is, of course, limited. So that's not exact, of course. It's just a very basic basis for this. You would have higher excited states in the basis you would need, but of course, you keep it like this. You would get a singlet ground state, meaning this psi 2, psi 3, these kind of 2 Slade determinants would dominantly form your ground state. But the ground state is then, of course, not a Slade determinant anymore because it's an interacting state. No, it's a difference between Slade determinants. And you would also mix in, of course, now in the full ground state, these ionic configurations because, as you easily see just from the Heisenberg principle, the system can gain energy or reduce the kinetic energy from our first slide when the electrons hop from side to side, forming these ionic states. So you mix in, to some degree, these ionic states, and those go, if you do the calculations, with 2T over U. And this U is the local Coulomb interaction that occurs if the 2 electrons share the same side. And then you have already the basic principles together. You have the hopping and the interaction, and those 2 key parameters more or less set the problem in interacting state. While this is still a very simple problem, and in this simple basis, you can diagonalize it completely, but it's not exact still. Yeah? You cannot solve the hydrogen problem exactly analytically. You can do it numerically, but not analytically. But still, it's a first step. And if you then continue to the lattice, we more or less arrive after some thinking of our beloved Hubbard-like Hamiltonian, which again carries the 2 important ingredients, namely the kinetic energy, scaling by the hopping T from the Heisenberg principle, and the local interaction which lives on each side. Of course, you have far-reaching interactions in the lattice also, nearest neighbor, next nearest neighbor, Coulomb interactions, but you can argue that those are usually much smaller than the local on-site interaction because there are screening effects, no? Because electrons come together and they try to avoid each other, and the whole system of electrons moves, so to say, to screen out electrons that approach each other too closely, and so creating some space charges in a simplistic light picture. So all the screening usually leads to the fact that far distant Coulomb interactions are screened down by a factor of 10, roughly, usually. Of course, there are exceptions, but this is the standard picture. So to a first degree, one can safely neglect interactions that are far distant. Okay? But still, then this Hubbard-Hamiltonian looks very simple, you would say. It's just an on-site interaction. You would think you can diagonalize that very quickly, but of course you cannot, because you will see that there are deep problems. Well, you can see that you can diagonalize, as we have realized very simply, this kinetic term, which just gives rise to the band theory. You can also diagonalize that very quickly on-site, on each side, because then it's just a quantum chemistry problem of hydrogen-like levels locally. So you can diagonalize one part in K-space and the other part in real space, but diagonalizing the full object, there's no good space, so to say, to diagonalize the full object. And so we have to rely on approximations, at least in the dimensions higher than 1. In 1 dimension, you can do that, but 1 dimension is nice, but especially if you look forward to realistic materials, it's a bit limited, as you realize. So in a pictorial sense, we have different regimes now that are governed by this Hubbard-Hamiltonian, depending on the filling, which means like electrons per lattice side. So the usually standard case where most of the strongly correlated people, so to say, first focus on is the half-filled scenario, when you have as much electrons as lattice side, so normally like 1 electron per lattice side. And then you would have this regime that the U is very small, that it would end up more like in the band theory regime. Well, if you would transfer this to realistic materials, it would say you can do a DFT calculations very nicely for that kind of system. It should work and give you a good result, like simple metals like sodium and so on. The other regime, extreme regime, is that you have the U much larger than T. But of course, importantly, is the T has still to be alive. No, if the T is dead, so to say, if there's no T, then you would just have isolated atoms, which would be very simple. No? But you should have to have the connection between the lattice sides. And then, very very pictorial, very simply thinking because of this interaction, which more or less, as we will write it down a bit more clearly later, it has a penalty, as we have seen in the H2 problem, of having 2 electrons on the same side. So the system will of course relax to a ground state where each side is just populated by 1 electron in this half-filled scenario, and they do not hop anymore. No? Because if they want to hop from one side to the other, they have to pay this huge penalty of U, which I don't like. So they stay, and the Heisenberg principle is somewhat suppressed in this picture. So this is the Mott insulator. That is another kind of insulator in addition to the known band insulator, where you just fill up bands to some level. So this is really a real space insulator, which in the end is a bit simpler to understand, but is even not covered in some basic solid state lectures, although it's a very important state of matter, of course, as you know. So in between, we have what I would say the most interesting regime of a moderated to strongly correlated system, usually like a metal then, where U and T are more or less on the same scale. And then, of course, it becomes most tricky because there's not a small parameter but we can maybe expand into. Most interesting physics, like superconductivity and other stuff that you know of course, appears usually in that regime when we have some inerrancy in the system and strong correlation. So historically, maybe also nice to look back, this was first more or less realized and described theoretically in 1937 by Mott and Peierls. So all this goes back to Mott historically in some sense, but actually it's not really completely true because there was Peierls, one of the main figures. So Mott has written that up, this note. So there was this finding of de Boer and Verwey that there is in nickel oxide this huge gap of 4 eV, which is not understandable from simple band theory. The solution they came up with, mainly Peierls came up with, is that just what we just said in other words, that if the so-called transparency, so this is the T, so if you ever have wondered where the label T comes from, that is this transparency that electrons move from side to side historically. And this, that then if the electron interaction between these sides is too large, then the electrons are prevented from moving. So that's just what we said, that's a Mott insulator. And so that is the first account of the Mott insulator in the literature. Of course, they have seen that there's no real mathematical treatment these days, but of course, these days we can do a bit better, as we will now discuss in more detail. So, but the next question is a bit, so how can we, what kind of physics do we expect? So far we have just treated this H2 problem, which is very simplistic, and we have seen it's dominantly in insulating state with some modified hopping. But of course, we have seen if you go to the lattice in principle, and we go to this interesting regime of correlated electrons, which are still itinerant and not fully localized, then, well, it gets very complicated and many interesting features can come up. And just to give you a bit of an idea, maybe a pictorial idea what is happening and what are maybe the important excitations and energy scales that we have to face in such a problem is, if you go to a real life problem that is very much in the same kind of spirit. So imagine you go to a concert. So when I was young, I was doing that a lot, but okay, this was a different time. So maybe you do that a lot. You come to a concert and usually come a bit late to a concert, because, well, anyway, you had to work in a lab, or anyway, it's not too cool to appear too early to a concert, so you come a bit later. And then, of course, all the people already gather in front of the stage and it's really occupied, but you have to be close to your beloved band. So the band has not yet started playing and everybody's drinking something, and you just move, you try to find a way to the stage, sneaking through the people. And that is more or less the problem that we are now facing. So you are at the entrance, you're the visitor, and you want to sneak to the stage. And you see like a smaller void of people, and you jump into that, and then you put a hand on the shoulder of your person before, and the person looks at you, okay, and it's not that start, I have my beer or something, they move. And you move, and the other people move. There's some person in the back sees, you're moving, so I'm moving with you. I also want to go to the stage. So there's a whole cloud of people. When you move to the stage, is also moving. And that is a kind of excitation that we have now in the system, which is this kind of quasi-particle that we also have in a solid. So in a solid, it's the same. But if the electron wants to move from place A to B, well, it has to talk to the other electrons around it to make its way, because there's not a free complete space available because there are other electrons. And that's an interacting problem. So that's the quasi-particle is moving. It's the electron, the visitor, that you add to the system, it's moving, but it's not the only thing that's moving because others have to move too. Yeah? And importantly, this is the excitation. Then it gets a bit like once you have fetched out how to make your way, you become, so to say, coherent with the mass, and you have more or less a straight way to the stage. Yeah? So you will go with a good K vector to the stage, so to say. That's your quasi-particle excitation. But there's an energy scale involved with that quasi-particle. There's a kind of a coherence scale that you easily realize. Well, if you go to a concert, you will realize easily. It's just if the band starts to play, so the light goes out and they start to play, and they start usually with one of their hits because they want to shake up the people, and all people try to jump, no? And if you now come a bit late, now you want to move through the stage. That is a bit difficult, no? Because no one cares about you anymore. They are jumping and yelling and everything. And you like to move and put hand on shoulder and say, hey, I would like, but you're stuck, no? Because there's no way to move anymore because you have lost the coherence with your other people, so to say. Yeah? So if the excitations around in the system are too large, you can picture that then in a physical way as a kind of high temperature, yeah? That people are excited randomly, maybe, by the music. And you lose coherence with the neighborhood. No one cares about you and you're stuck. You cannot move anymore. Well, I experienced it a lot of times when you come too late and then you have to stay where you are because there's no way. So there's a coherence scale involved with that quasi-particle excitation that usually goes at a certain kind of temperature, and if the temperature is too high, you kill the quasi-particle and you localize the electron. So these are kind of excitations that go on in a correlated metal. There are many more. Of course, you can have more like concerted like of movements, as you know, ordered states and all that. But a lot of excitations going on in this system, and you see they go with a certain energy, they go with a certain coherence, they also go with a certain time, as you see. And all this have to be described nicely by a theoretical approach. So how do we do that? So then we have, again, another picture, which is the best kind of approach to do so, to describe all that nicely. And these are the two kind of descriptions that I call usually landlord and private investigator, what that does mean. So that is the second picture, and then you're free from this picture. Sorry, then I will move on to more concrete terms. So the picture is that what we did in the H2 problem with our Slade determinant is more or less this view one. It's a landlord view, so to say. You look on the lattice, and you want to find out about, picture the lattice as a house of tenants, and you want to find out information about your tenants that live in and what they are doing, and if they're doing right or wrong or something. That is like how to understand the full lattice. It's in a landlord view, you have all the data about your people that live in this house and what they're doing, you have all the records, and if you want to have information about it, look at this. It's like a landlord, even like a God's view on your lattice or on your house of tenants. But this is very difficult to get, yeah, because as you know, God's view is not easily appreciable by us, so it's very difficult. And there would be another way to get the same kind of information of what's going on in your house in this, let's say, private investigator picture, when you like sneak into the house and just rent a room there, and you take some time to go around the house and visit other people on the stairs and so on. You know which people live where, and there. With time you scatter with the people. And by time, you will also find a lot of information about your house and about the people that are living, what's going on in this house, or again, physically, what's going on your lattice. So these are these two kind of complementary views. So this is the standard view that you learn early on in course system, that you have to diagonalize and fully understand the system right away, at once, completely, which is nice to do, but usually doesn't work so nice in real world because systems become too complicated. If you go beyond H2, things become too complicated, even in an approximative manner, because the Hilbert space scales so quickly, so largely that it's impossible. Whereas this is much easier to implement theoretically, because it just involves one particle, so to say, that scatters with its surroundings. And as you will see, this is much easier to tackle theoretically. But as you see, it takes time. So there's a time scale involved in that description to get information, which is not right away involved in that kind of picture. So this second picture, which is in this house-like tenant picture, is the private investigator, is the Green's function formalism that we now will remind us a little bit about. And this is just a kind of theoretical scope that is now also most tailored to be used when one wants to understand dynamic mean field theory. And mathematically, you implement this private investigator picture in this kind of structure. So you generate a particle at some point in space at some time, and you propagate through the lattice to some other time and space, and you are destroyed at this very point in time and space. And then what you have learned in between, you can analyze in a spectral way, or just by doing a concrete calculation, as we do here, for instance, for the non-interacting case. Yeah? So let's see what this Green's function gives us. So usually transform first to a K basis from your real space basis, and then you would interpret those operators in a Heisenberg-like manner, and then you can most easily do this calculation. If your psi 0, which would be your ground state, is the non-interacting Fermi sea, then the calculation is very, very simple. And I guess some or most of you have maybe done this also in courses. If you do this calculation very simply, you get then this kind of Green's function, which goes with an exponential and some theta functions. And if you then do the Fourier transform to a frequency, which can also be done right straightforwardly, you get this fraction with 1 above and the dispersion of your band electrons and the frequency omega. And you need this small integrating factor to make the Fourier transform nicely defined because of these time oscillations. Yeah. So that is your non-interacting Green's function of free electrons. Yeah, but those are not yet already the electrons that scatter with the other people or the other electrons. So you have to do a bit more because this is just a non-interacting limit. Now, to crank up the interacting scenario, you would theoretically do a bit of a mathematical tour de force to see that, but in very basic manners, you can think of it as of this scattering problem that we were just describing at this person at a concert scenario, that you come in and do not interact, but then you scatter with some kind of persons or other electrons, and this is condensed in this sigma function, and then you propagate again without scattering, and of course it can then have multiple scattering events and so on and so forth to any kind of order. And if you want to write this a bit more in a simple manner, this is this Dyson-like description, which you can easily realize that it's the same kind of description when you here have an implicit relation between the full G on the right side and on the left side. And you can easily formulate this in this writing by bringing this to the other side and isolate G, and then you can easily see that you can write again as this kind of fraction times G0, and you isolate again the sigma and the G0 minus 1. And G0 minus 1 we have just computed as that object. So in total, the full interacting Green's function has a very kind of similar structure as the original non-interacting Green's function, with just a caveat that now we have to take care of these scattering events condensed in this sigma function, which is a self-energy. It's k-dependent and omega-dependent. So it describes the full glory, so to say, of the interacting problem. So if you know the correct self-energy, you have solved the full problem. Maybe you've learned the DFT tutorial. There's a similar saying in a DFT account that you know the exact exchange correlation function, you also have solved the full problem. In some sense, these are the same kind of leveling, although there are some differences, but anyway. So this still is the most general way of describing interacting electrons, knowing the good self-energy. And now the whole task of getting a good description of strongly interacting electrons is mainly to find a good approximation for your self-energy. And there are various ways to do this, and we will talk about this, and we'll find out that DMFT is a certain kind of theory that gives you one especially nice representation of this self-energy. But before that, let's still think a bit about what's all living in this self-energy. So usually then one writes this down in this kind of diagrammatic sense, which is more or less just a diagrammatic translation of these analytical formulas that we have seen here before. So you have multiple scattering events with the sigma again, and then if you really crank down what is in sigma really encapsulate, of course it's the electron-electron interaction, and that can be also written pictorially in the Feynman diagram sense. This is done here, and then you would have different kind of scattering of an incoming and outgoing particle to different kind of orders. So these two first diagrams are the most simple one. These are the so-called Hartree and Fock diagrams. Well, that's just a Hartree-Fock approximation that you know from early, advanced quantum mechanics, I would say. These are important diagrams, but then you easily realize this is a very simplistic approximation to your self-energy in the end, because you just take the first order diagrams. There's also some limitation that you see that they do not really have a time dependence or frequency dependence. They have a bit of extension in frequency, but this is just an artifact of the simplistic kind of scattering events, which we will not discuss in detail. But you see that these higher order diagrams, they have a unique, so the time axis goes along the C axis. So it's more written here, so time goes along C, so at a certain time, there are interactions happening for these higher order diagrams where they are not happening for these first order diagrams. So Hartree-Fock is still a nice kind of approximation, but it's a very simplistic one, which, as you maybe know, which we can tackle later on, for instance, goes into this DFT plus U scheme. So DFT plus U in the very end is nothing else as Hartree-Fock on locally interacting electrons. That's okay in some limits, but of course it's very, very restrictive. And you would do better to have this frequency dependence, because as we have learned in this other picture, this is just the private investigator goes around and likes to know about the system. There's a time scale involved with all these interactions and scatterings, and that is encapsulated in this time dependence, or then of course in the Fourier transform in the frequency dependence. So we would like to have a frequency dependence on our self-energy, which again is not there in Hartree-Fock. Of course, so the question is, okay, how do we then really go to a good representation of the self-energy in that kind of strongly interacting regime? Well, that is then exactly a bit difficult, because you would simply think, well, I have to add up all these orders, so I have to go to Hartree-Fock, and then I add other orders, and then I eventually come to the good self-energy for my strongly interacting system. But one realizes that is not really the best way to do that, because one realizes very quickly, if one looks a bit more in these properties, that in the end, most of these strongly interacting problems depend to all orders on this kind of diagrams. So you would need to include all kind of orders, or you would not need to know where to stop, which kind of diagram is important. Should I stop at the hundreds or the thousands diagram or so on? So you would need to go to all kind of orders to treat this system. So you could, for instance, take this first, second order diagram. So maybe some of you also know that. This is also an important one. This is a so-called RPA diagram. So that's the next step beyond weak coupling. So there's some frequency dependence. It gives you a weak coupling approach to strongly interacting systems that many people use also in modern research, which is a very still powerful approach, but it's also very limited. It's just a second order diagram. So it cannot describe strongly interacting. It just can describe screening processes nicely, some particle hole excitations in a limited way. That's okay for some, let's say, semiconductors, where we will know that this RPA goes into GW, and then you can describe band gaps a bit nicer. So that is okay, but it will not give you a good description of the strongly interacting Hubbard model, for instance. So there we have to do much better. So the question now is, so how do we end up at a good self-energy? What's the best strategy to do so? So adding up diagrams is not a good strategy to go to the strongly interacting regime. We have to take another kind of perspective to find a better approximation for our self-energy beyond Hartree-Fock and beyond RPA. Therefore, what one then does, takes a different kind of vantage point, and one looks at certain limits of your problem and hope to find solutions in certain limits. And if one understands certain limits of your problem, one can then hope to find maybe a kind of extrapolation or interpolation to some more interesting regime. So this is again the writing. So we want to find the good self-energy, and we get stuck. This is the most important regime for at the moment. At half filling, we have our beloved Hubbard model now written out completely by the band term and the locally interacting term as you know it. So we only take, of course, one orbital only and nearest neighbor hopping, so the most simple way to how to write it. And then we again face these two limits that we have already talked about a little bit. although here with a bit of a different kind of twisting. So this is this non-interacting limit when we put u to 0. So that goes into our G0 of the Green's function description. So that would be the ideal metal or Fermi gas with density of states just around the Fermi level. The other regime is not right away the mod insulator that we've talked about before, but we made it even simpler. We go to the atomic limit where we put the T, the hopping, to 0. So then we have disconnected sides, and the problem is even simpler because now we can diagonalize the problem on each side individually and just add up all the individual solutions to the full solution because they're disconnected. So we have decoupled lattice sides and only single occupation. So we get a hydrogen-like spectrum of your single level when you just have one electron on a given site. Or when you put 2 electrons additionally, well, of course you would have to pay the penalty U. So in this one particle spectral function that I'm plotting here, you always get the energy over 1 electron. So we get this level energy plus U per electron, so to say. So these are the limits, and the interesting regime we just have talked about it is in between when we have U and T both alive. And so we more or less try to maybe very vaguely try to interpolate between these regimes in some or the other way. And we would like to do this, of course, in the best way that is possible. And it has to be also most simple, of course, because the exact solution is not tractable anyway. So we start to do so. We start from some strongly interacting limit that are closest to our understanding, which is this atomic limit. And we will not start from this limit because this is a weakly interacting limit. So we will not like to go from there to there because that's a long way to go. And anyway, we are interested in the strongly interacting regime. We look for a self-energy in the strongly interacting regime and not in this very weakly interacting limit. So we try to find 2 scenarios that already live at a sizable interaction, and one is the atomic limit, and the other will turn out to be the mod insulating state, where we can also hope to find a kind of perturbation around this state. So these are now a bit these 2 kind of slides that I talked about, which are a bit more with equations coming, but it's not so important that you follow all the details of these equations step by step. It's more important that you get the basic idea what's going on and how we then can end up with this at some way to find a good strategy to get a better way for the self-energy. So if we want to look in the atomic limit via this Green's function technique, it's best suited to take the spectral representation of Green's function. So this is very easily, so this looks a bit complicated, but let me just go back to the so that you see what is happening. So what we're doing here, we are shifting, inserting a 1, so to say, quantum mechanic, a 1 of all many body states that are available. You know it's a complete state, so it's a 1 in complete representation. We insert that here and do already a Fourier transform from time to frequency. So we end up with all these kind of denominators. And in the numerator, we would have this 1 inserted, giving rise to various kind of expectation values of your operators, of your creation, and annihilation operators with the ground state and this respective excited state. So this is the so-called spectral representation or Lechermann representation of the Green's function. And that is the best, is a good way to do so in the atomic limit because we have only such limited number of states that we have to account for because it's just the atomic limit. It's an isolated problem of an individual atom where in the end we only have 2 possible scenarios how these Green's functions or respectively the operators can act in this Green's function. Well, first you could have, so to say, this, since it's spin up, we look for spin up. So the spin up state is occupied locally. So with one electron, you can destroy that and you have a 0 state, an empty state. So that would be more or less this kind of part of your Green's function, so this first part. And of course, it scales with the number of occupied spin-up state, which would be 1 minus n spin down. The other way that you can excite the system by creating or the annihilating electrons is that you have already a spin down state occupied, obviously, and you create a spin up state. And you go to the 2-particle state for the atomic problem of 0, 1, and 2 occupation possibilities. And this is the second part of your Green's function. When, of course, then you have to pay the penalty u, and it scales with the number of already occupied spin down states. Now you can do this integration with frequency because there's now, of course, a freedom in frequency that how you can do so by this Fourier transform. And if you do a sum up these integrals, you get these two contributions that we just have talked about via these two kind of fractions. So that is just the Green's function of the free atom, so to say, with one orbital. Yeah. Now, of course, you would like to rewrite that kind of Green's function in a standard manner, as we have just seen before. Well, maybe let's go back to see that once again. So our standard writing of the Green's function was in that framing, yeah, that we have the omega minus the non-detecting dispersion and the self-energy. Now we have it in this bit more complicated way, but we can easily write it by just enforcing that it has to be this kind of structure, and we just rewrite it analytically that we have it in that form mathematically, and then we can identify the self-energy of that atomic problem, which is not, the physics structure is not so important at the moment, it's just that you can do so, and you would have a self-energy for your free atom. Yeah? And that would be well, the free atom, yeah, Green's function, that's nice, but of course, that is not really super interesting. The interesting fact would, of course, be the aspect that we have now a certain form for the self-energy, which is then of atomic kind, but we could maybe use that atomic self-energy in a crystal calculation. Yeah? So that would be one way of doing a first approximation to our strongly interacting problem, that we just use the structure of the self-energy via these occupations of different spins projection and decorate with the U. So to use that in a crystal calculation, and we just enforce it that the self-energy should have that structure for a crystal calculation. Yeah? Just like choosing a very specific form of an exchange correlation function, so to say, which has the atomic kind. Of course, it will not be very good. That can easily be seen because it lacks all the information about hopping process that you would like to have, but it's a first approximation, and it's called the Hubbard-1 approximation. Yeah? And what it gives you is also not so surprising. We more or less smear out these two excited states that we have in the problem. Yeah? Remember, going back to this, we have these hydrogen-like levels for the free atom, and they more or less smear out now two kind of bands. But these are not non-interacting bands, as in our beloved band theory, but those are the so-called Hubbard bands when we create holes or double occupations, and they wobble around on the lattice in a very irregular fashion. So they don't go with a good K vector, they're not very coherent, they have a very short time scale because they're very broad, and they live on a high energy scale, yeah, but that's fine. Well, it can maybe describe some way of some mod insulator, if you like. That's okay, but of course we lack states at low energy, so we don't have reached this interesting regime of a correlated metal because this is not a metal. It has not any states at low energy where we would have a zero here. It just have high energy states. So this is our first approximation of the self-energy, but obviously it's not a very good one, at least not generally for correlated metals. Yeah? It may be still better than DFT plus U, yeah, because you get some lifetime effects and many body effects on your Hubbard bands, whereas if you do DFT plus U, it would be just a shift of your infinite lifetime DFT states to higher and lower energy. So what is a starting point? And let's go to the other kind of problem to get a different regime where you maybe find additional structures for this correlated metallic regime. So this you can now look as an approximation around the mod insulator. So how we do this, again, with the other kind of twisting in theory, such that we go to the problem of infinite U of the Hubbard model. So we take a lattice and we assume that the U is infinite. Well, we can do that, of course, since you're a theorist. So what happens then? Well, of course, you will suppress completely a double occupation on the lattice, yeah? Because there will be no electron hopping by any means to any other lattice side. That will not happen by any other means. No? So you write this Hamiltonian in such a way that you add these projectors that completely project out double occupation on states. And, well, that would be possible. It describes a mod insulator. Now, of course, you could think what happens if you slightly dope the system And we would still suppress most likely double occupations, but then we would still have a more tractable analytic solution of the problem. And then what's usually be done in a very easy way to tackle this is done by this auxiliary boson-like description. So we rewrite the electron operators by two different operators. One is the F particle, one is the phi particle. So what does that mean exactly? So we already know that there are two kinds of excitations on our lattice, meaning that there is a local excitation, this comes from this atomic physics, and there's a low energy excitation which we expect comes from the hopping electrons, from the quasi-particles that we've talked about. Now we can decompose these kind of excitations already on the operator level via this construction, where this F particle should carry this quasi-particle degree of freedom of hopping electrons, and this phi particle should carry more or less these high energy excitations. Yeah? Because when we add holes to the systems or empty sites, then there's a way that the electrons can hop to the sites. But we have to keep a bit track of these empty sites. Yeah? So how many of these empty sites are available? All this is usually fully described in the full problem, but to keep it manageable, it's a good idea, a good strategy to give an explicit degree of freedom to these empty sites. And this is done in this way, that if we create one of these phi particles, we more or less create such an empty site. So the true empty site in our problem is not a zero object, so to say, but it carries this phi particle. It is a boson, because it has to be antisymmetric, and this is a fermion, so this is a fermion, so this has to be a boson to keep the statistics correct. So when we have empty sites, so to say, we have not nothing in our system, we have these phi particles in our theoretical thinking. It's just kind of a bookkeeping of the empty sites. Yeah? And if we work around this kind of strategy, then we can have also a nicer way of describing this constraint of not having double occupations, which is a strange kind of constraint because it's saying we should have occupations smaller than 2, sorry. But using these phi particles, we have, of course, either we have electrons on the side, 1 or 2. Well, 2 we don't want to have, at most 1. But if you have no particles on that side, we still would have something, meaning empty sites, and they all add up to 1 in this constraint of the infinite U problem. Either we have an electron on the side, or we have the empty side, which is a phi particle. And that is a nice way of constraint for our problem. We would need to enforce this constraint, of course, on each lattice side I, and then everything would still be exact. And we can rewrite the Hamiltonian in this manner, and it would all be nice. Yeah? But surely, well, life is not perfect, and would be still very, very complicated to do so, because you would have zillions of constraints to be enforced on each lattice side on a thermodynamic limit. So we do something simple. We treat this constraint on average in a mean field-like fashion, and say that we want to keep it such that on average this constraint should be fulfilled. And another way of saying this is, in a more fancy way, is saying that you condense these phi particles of bosons, well, to a condensed boson phase. And then you have average values of all this, which still at 1 throughout the system. But the nice feature of this simplistic description is that you can see that the effective Hamiltonian is such that if you rewrite the hopping term very easily via this decomposition in the original way, but in the approximation, since those phi's are condensed, now you can take them out of the sum and they are just numbers, and they scale with this R square and in front of the T. And then you already have a very simplistic idea of band narrowing, because if you have no empty sites at all, well, then of course this would be 0, obviously, and you would have no hopping at all. If you have some numbers of empty sites, you would have a smaller value than between 0 and 1, and you would strongly normalize the T. This gives you the band narrowing effect. It just means, of course, that electrons like to hop, of course, but if there's another electron on the next side, they don't like to hop, but they only like to hop if there is an empty site close by, and that is then described by this strong renormalization here of the hopping parameter, which then gives rise to this band narrowing effect. Now we can go through the fuller description. Of course, in the end, we also would like to write down a Green's function, a self-energy for that problem. Yeah, that is, of course, our strategy, as we've done before in the atomic limit. So we have to write down a full free energy or a grand functional with this constraint taken care of by a Lagrangian multiplier. And then we minimize this problem, and then we get a solution. And we can also write this in terms of a Green's function. Well, because we just write it first for this F particle in our usual kind of strategy, in that way. Because the F particles obviously do not interact in our way, so we can just write them without the self-energy, just while they are dispersion. We just have to find out the dispersion of these F particles. But this is very simple because we can just define them as a derivative of the energy of our function with respect to the occupation number of that particles. And then they go with a scaling as expected of the original dispersion plus this Lagrangian multiplier. So we insert this and we get a Green's function in the standard way for these F particles. How we want to have a Green's function for the full electrons, and that is not so complicated. Either way, we can just use what is the decomposition of C's into F's and Phi's. So that would be, well, you would have to tweak the F dagger and the F, but it would be some form then of the Green's function. So you would need to add this factor of R square to the GF Green's function to get the full Green's function. That you can do. And then you can rewrite it again in terms of a self-energy by just bringing this structure in the standard form of 1 in the numerator and everything below in the denominator. And then you find a self-energy of that kind for your problem of a weakly doped mod insulator, which is completely different, obviously, from the atomic limit. So now you have a frequency dependence also, which you had also in the atomic limit, but it is such that you have at low frequency, it goes linearly with that brace here. You have also a static term that takes into account of some shifting of states. But this describes now something completely different than the atomic limit. So with finite R square, which is more or less nothing else as a doping, of course, of holes, you describe a Fermi liquid with a linear in frequency dependence, which is, of course, a limiting description of a mod insulator in an idealist fashion, but still something where you would now have, when we go back to our picture of spectral function, you would get a peak right close to the Fermi level, which is this Fermi liquid of linear frequency dependence. You would not see anything of these high energy excitations. So these are these two limiting forms of the self-energy that we got from these two perspectives. One, the Hubbard 1 kind of picture, we get high energy excitations and no states close to the Fermi level. There's no metal anyway in that description. Or the doped mod insulator, which describes a Romanized Fermi liquid with only a peak at a Fermi level at some finite doping and no high energy states. So both views are, of course, not complete because they miss out either on the high energy or the low energy regime, but apparently they are a bit complementary. Yeah? So we would think or hope that with this kind of two limiting calculation, of course, it's nothing ensured, but we would hope that we have already more or less qualitatively gathered the main pieces of what we need for our interacting regime. Yeah? So that would be the conclusion, so to say, at least on the structure of spectra that you would like to see in a correlated metal, namely this kind of three-peak structure. So we would have this renormalized high energy excitations, which come from the atomic limit. Your atomic excitations or quantum chemistry excitations, which still live, so to say, on the lattice. Yeah? So they're not completely gone as in band theory, but they're still there, but in a very irregular fashion. And a renormalized peak of your original very dispersing electrons, but at the Fermi level, again, now strongly normalized because double occupation is not completely suppressed as infinite U, but to some degree, of course, suppressed. So in other words, we would like to have a self-energy in the end that can describe that structure. Obviously, this Hubbard 1 description or this auxiliary boson description cannot do that. They are nice approximations in their limiting framing, that's okay, but it's not a very general thing that you would like to use for very open kind of calculation for your system where you do not exactly know what in the end is the physics of your material, so to say. So the next step is, of course, to think, okay, how do we end up at a self-energy that more or less can describe this three-peak structure? And that, of course, is now finally the DMFT idea. So to go into this. So first, but the strategy is now clear. We should find a self-energy that describes this energy dependence, because energy dependence is the key to that. We have to describe the low energy regime and the high energy regime. And it has to be frequency dependent, obviously, for that sake, because, well, obviously energy dependent. So we need frequency dependence for sure, that's for sure. Now we know in the exact self-energy, we also have K-dependence. So the next question would be, do we also need K-dependence? Well, we didn't have K-dependence in the Hubbard 1. We didn't have K-dependence, obviously, in this auxiliary boson description. So can we be saying that maybe the K-dependence is not so important at all, or do we still need it for this three-peak structure together? So this is the first question to ask. Should we continue with a frequency dependence only in our self-energy and just work on a better self-energy with a better frequency dependence? Is that sufficient? And well, there was then this first idea, so to say, the first original work in the context of DMFT done by Metzner and Vollert, and saying that in fact there is a good limit with no K-dependence, which is this kind of infinite dimension limit. Yeah? So Metzner and Vollert told us there is in fact a good limit with all complexity still of interacting problems for the self-energy, which has only frequency dependence. That is a limit of mean field kind, where we have infinite dimension, where you know that also in static mean field theory of Weiss, ferromagnet, for instance, is also exact in infinite dimension. And that also holds here now in the for this electronic problem, where it's not a static form as in Weiss theory, but it has a frequency dependence, but the K-dependence drops out in that limit. So that ensures us, or gives us hope, that we can use that infinite dimension limit also for our realistic systems, which live in D2 or at least in D3, it should be okay-ish, to live with that approximation. So we drop K-dependence, making contact to that exact relation. Okay, so the next step is, okay, now we can have a signal with only frequency dependence, but how can we do better than the two approximations that we had before? Well, then there has to be an idea, because what we are of course missing is a correct, let's say, embedding of our self-energy. It's best understood from this atomic limit kind of self-energy of Hubbard 1. There we only took the self-energy of your free atom. And that is of course a bit bad. Now, just remember back this Heisenberg principle before. Now, there we have learned that if we restrict the electron spatial distribution to a very limited region, then the kinetic energy piles up tremendously. That is not a good state. So the system would like to dissolve or would have some region to dissolve or absorb this high energy that you would get from keeping an electron to a local spatial region. So the idea is that you then focus still on a single lattice site, but embed it in a bath, that absorbs more or less this high kinetic energy that you would have locally from putting the electron aside. So that the electron can hop into this bath and disperse and give credit to the Heisenberg principle, so to say. So this is the basic idea, that you find a better embedding for the self-energy when you started from the atomic limit. And you describe it in this impurity kind of construction. So you now define an impurity Green's function in that manner, just as we did before. We know that the whole structure of any kind of Green's function is that way, one above, and the denominator with omega, where we add also chemical potential. Then we have a self-energy that is associated, has to be, as before, to that problem. And we have some kind of kinetic energy part, which I just write here as this E tilde, which is not a lattice because it's a bath, but it's just like some kind of energy, kinetic energy kind of part that takes care of this wish of the electron to dissolve its kinetic energy. And that is then defined by this. So this is an exact relation. It's just a definition in Green's function terms of our problem. And obviously, we can just rewrite this. We just name this here, this prefactor of first part of this denominator, this G0 minus 1. And then we have this new kind of description, where this is obviously also a kind of Green's function, then without a self-energy. We write this as G0 minus 1. It would be like a non-interacting like Green's function. It's not a true Green's function that we can use now for our solution, but it's kind of a model like of bath-like Green's function, which describes our bath, obviously. And there we have defined now this impurity problem, where we hope that within this construction we find a better approximation to our self-energy for the lattice. Now here it's still living on an impurity, and it is subject to this Weiss mean field, which is now also frequency dependent, as you see. Yeah? Now the next question, well, of course, first of all, we can say, well, this kind of construction, maybe it's reminiscent of what we do in Cone-Sham-like theory, where we also map to an auxiliary virtual system, as you know, where we even have a good reference system, the homogeneous electron gas, which we do not have here, so that is one problem. But it's same in spirit, obviously, no? That we map the problem to an auxiliary problem, which gives us enough freedom to find a good solution, so to say. Now, by this writing and this definition, the problem is exactly defined, so we can solve that problem exactly. Yeah? It's a full many-body problem, so we would have to solve the full many-body problem of electrons interacting here in time and hopping to the bath and coming back and all that. So it's a full many-body problem. But it's doable because the number of degrees of freedom is very low. It's just per side still. And the bath function just comes in as a bath function. That can be treated rather efficiently, for instance, in quantum Monte Carlo. Yeah? So this problem is still not super easy, but it can be solved by available numerical schemes very, very straightforwardly. So that's fine. But of course, since we use this as a helping construction to find the good self-energy for the lattice, it is not yet sufficient because, of course, you wonder, okay, when I want to use this, what is the correct Weiss mean field function for my lattice problem to get a good sigma to use then in the lattice problem? That is still not given here by this idea. So you need another step to reach that kind of information. And that's the second or third step in the dynamic field field theory. And of course, you say, well, of course, in the end, I want to use this kind of picture of my impurity construction to have it as a constant mapping between my original lattice problem, where I have a U on each side. So those should be more or less describing the same kind of self-energy. Yeah? Just as in the DFT world, the density of electrons should be the same in the Cone-Sham system and in the original system. Whereas here we focus on the self-energy. Now, how can we do so? Now, the self-energy, of course, here is k-dependent, so it cannot be exactly the same here. But we can use it as a constraint, such that we, on the other hand, focus on the Green's function. Well, because the local Green's function of my lattice problem, when I sum over all k states, where I get a local Green's function, is of course reminiscent of my impurity Green's function in this impurity construction. And this is the DMFT approximation in the end, that this full local Green's function of my lattice problem with the full k-dependent self-energy, in principle, should be identical to this impurity Green's function in my construction. And that is the helping step that defines more or less my Weiss mean field. Because in the very end, then, I have then obviously a kind of a local DMFT Green's function where I describe the self-energy via this constraint, via the impurity self-energy. And to define the Weiss mean field is now quite a straightforward task. You do it as also in DFT via a self-consistency cycle. Yeah? Just remember in DFT, for instance, you can also start from some atomic charge densities and you do iterations in the self-consistent Cone-Sham cycle, where in the end, your charge density, of course, converges to the good charge density, which is, of course, not the atomic charge density anymore for a lattice problem. And the same is done here. So we start with a given Weiss mean field at our will. We enter this kind of quantum impurity calculation. Remember the full many-body calculation for this impurity construction. Yeah, we get a self-energy out of it, obviously, and then via this basic relation, which defines our problem, we can then insert, so to say, this self-energy in our self-consistency construction, where we enforce it should be identical to this G log Yeah, we can compute this G log, and then we can construct a new Weiss mean field via this basic relation again, which will be then different, of course, than the original Weiss mean field, because it now carries first self-energy effects. And we will do this, this loop as long as it's self-consistent. Yeah? So as long as the Weiss mean field, for instance, doesn't change anymore. So then it has coherently adjusted to our given lattice problem. So it always has to be adjusted to that. So in the end, you see the Weiss mean field is a quite of a complicated object, because it's a kind of a non-interacting kind of Green's function for the impurity, but of course it carries all the other U's, so to say, from nearby sites. So it's still a quite complicated many-body object that describes your problem in this auxiliary way. And that's more or less DMFT, no? That's what you have to do in a DMFT calculation, and well, and from that on, we get all kind of good solutions we can discuss in the next slide. Before we want to do that, I want to still put my finger on some aspect which I think is important, is a bit put under the rock in standard treatment of that theory, which is very important, which is the temperature dependence. Remember that basic picture that we had at the beginning of this quasi-particle scattering in this concert picture, and then you raise the temperature and the quasi-particle stops and it gets trapped and so it's killed, so to say. So all this is naturally also included in DMFT when we do temperature-dependent calculation, yeah? Because the temperature is a very vital, natural kind of ingredient usually in a DMFT calculation. Of course, you can restrict it to t equal to 0 also if you like that, but quite naturally, especially if you do quantum Monte Carlo for this impurity solution, you naturally have a temperature in your system. Yeah? And that is then, okay, this is a bit technical, but just that you see what is so has to be done to solve this quantum impurity problem, also then here with temperature. So you would need to calculate this local or impurity Green's function. And you usually write this best then for your quantum Monte Carlo in a path integral writing, yeah? When you have to integrate over your local C operators, these kind of Grassmann variables. Again, this goes a bit very into technicalities, which is not so important to understand the basic principles. And you have to weigh it with your effective action, which is described by your Weiss mean field, obviously, and the local interacting part. And it's all dependent on time. Yeah, whereas the integration is from 0 to beta. So this is the Wick rotation that you have to do when you do finite temperature Green's function. That well, this is something which one should look up then more in detail if you're more interested in this, in finite temperature, many-body formalism. That this is the path integral going from 0 to beta. So temperature and time have an intrinsic link in quantum many-body theory by this Wick rotation. And if you go to 0 temperature, this integral would be becoming much evolved, so to say. So, but if the temperature is a bit higher, so to say, in DMFT, then the calculation is even faster. Yeah? So temperature even helps you in the calculation of DMFT because its integrals become not tractable. Because you have to discretize this in some way or the other to, of course, compute this numerically. But once you have done this, you get a Green's function which would live in this tau, which is this imaginary time of the Wick rotated description at finite temperature, and you will get kind of new frequencies, which are now the so-called Matsubara frequencies, which again are nothing else as describing that you now have a Green's function which takes into account finite temperature. Yeah? So if you see this in papers, and some people are like distracted, what does it say to me, Matsubara? I have no clue. So this just tells you they work at finite temperature. And you can also still do analytic continuation to a real frequency if you wish, but still the full information is already gathered on that level, and you can analyze all the physics, most of the physics usually already in this Matsubara space of self-energies and Green's functions and so on. And therewith you get all kind of important features of finite temperature, which you would not get just from a Fermi-Dirac-like manipulation of change the statistics of occupied states as you do in a very simple account of finite temperature. So this is done here a bit more in a involved sense that you can now describe also these coherent scales and fluctuating local moments and all that you would like to have also in what you have in experiment also at finite temperature. That is all included usually in DMFT right away from the start. You don't have to bring that in by some other means. I think that is important and should also be always kept in mind. And then, of course, you can get all the physics that you like to have in a many-body system. You can now describe the correlated metal with that self-energy that you gather from this framework. You can describe still a mod insulator, in principle also the weakly correlated metal, but of course that would be a bit huge work to do so. We can get that from simpler methods. You can get all these finite time scales, the lifetime effect, coherent scales that we have talked about. So you can really kill a quasi-particle by temperature. You would see that the peak would disappear with temperature. You can have local moment physics. You can describe paramagnets. Yeah? As you know, in DFT, you can usually not describe paramagnets. You can describe non-magnetic systems or ordered systems. Yeah? But here you can really describe the fluctuating moment, and you can also compute Néel and Curie temperatures. You can also describe ordered phases, like in standard mean field theories by introducing a sublattice, for instance. Yeah? Also, you can describe non-Fermi liquid features, yeah, that is also included because you have the full frequency independence of self-energies in the self-energy. So it's not only linear as in this Fermi liquid solution for our dope mod insulator in the simplistic manner. It can be also more complicated. It's not linear, but maybe logarithmic or something. You know, this is all included in DMFT already. Depends on your problem, and of course, much more. But of course, there is a restriction that non-local physics is not included because we have, by this construction, we have neglected the k-dependence. Of course, there's a price to pay, so it's not a full thing. It's just living in this infinite dimension limit of no k-dependence, that all the correlations are dominantly on-site and do not depend on the hopping directions of your electrons. It's a limitation, but especially in D equal to 3, it usually is very comprehensive. Of course, there are exceptions. Maybe you not know of such exceptions, but yeah, generally it's working nicely all over the range of systems. And then you would have this standard kind of picturing of a system from a weak correlation with a small u, and then you crank up the u, for instance, with a fixed t, and then you enter this correlated metal regime where you form this renormalized dispersions and these sidebands of Hubbard excitations of your local atomic-like excitations, which are still there in the system. This gets, of course, smaller and smaller, the width of this peak, so to say. And then in the very end, you end up at a mod insulator. Yeah? That is then the full range of correlation that you would like to have and can describe in DMFT. Now, of course, then there come in, of course, lots of technicalities of the method, which I will not tackle because this goes now into details of the method. No, I mean, once you have understood the basic principle of the method, you can work yourself into these details or running a code on your own and all this. So, of course, there's, as we have talked about, this heart of the problem is this quantum impurity solution, which you have to solve still at each step of your DMFT iteration before self-consistency is reached. And there's a whole flavor, multitude of different kind of ways to do that. I talked here mainly about this quantum Monte Carlo, just in talking, not in fully addressing the scheme. But there are other schemes like exact analyzation, some kind of second order-ish kind of treatment. This is called flex. Then also there are DMRG solvers. We have heard about DMRG already in other contexts in the conference, but also this can be used as a solver for this quantum impurity problem in DMFT and many more. Now, there are some technical things like a mixing between these iteration steps, which you also would need in DFT. This is usually very simple. Here in DMFT, it's usually only a linear mixing. Then you can generalize the whole problems. Of course, the more interesting stuff like multi-orbital Hubbard models, Holstein models with phonons. Of course, as you know, this has all been done. Of course, it's the current research that we're all doing on this now. But this is more or less straightforward to do. It doesn't really change the structure of DMFT. It just changes your integrating Hamiltonian, the Hubbard Hamiltonian, and it changes, of course, your correlated subspace, which is not only one orbital anymore, but more orbitals, yeah, like a full D shell or something, but the whole structure of DMFT remains the same. But then there are also extensions to DMFT, which of course is current research, ongoing research, like you would, of course, like to bring in for some problems which are very, very demanding some K-dependence in a self-energy. And this can be done in various ways. One way is called cluster extensions. It's very simplistic that you not have a single side as an impurity, but a cluster of a plaquette of 4 sides, for instance, for a square lattice, or triangle for a triangle lattice, and so on. So that you have some short-range K dependence. Yeah? There come some issues with this, like translation symmetry breaking, which you also would have in quantum chemistry problems. But again, these are it's not all straightforward methods. There's always a caveat with these methods because it's not so easy. Then you can measure the vertex in a for the two-particle Green's functions. Once you have found a DMFT solution, you can measure the two-particle Green's function, get a vertex function, and by this compute lattice susceptibilities beyond RPA, for instance. You know that RPA, as we have discussed very quickly, describes the dressing of the electrons from screening effects, and then you can have a Lintard-like of susceptibility, but you can go beyond this by using these vertex functions, for instance. You can also use this vertex in a full extended DMFT spirit, where you have a self-consistent scheme, which then brings in K-dependence from this vertex, and you can expand the self-energy in K-space, so to say, with the help of the vertex function. So these are called dynamical vertex approximation, or dual-Fermi, or other flavors, which go beyond DMFT in principle. But those are up to now limited still in the range of applicability in terms of number of orbits that you can use and all that. Of course, they're very numerically very demanding, as one easily realizes, because already DMFT is a bit demanding, and this is of course much more so. And then of course there's this combination with density function theory, which is like one of kind of workhorse we have now in material science even, yeah, that you can do DMFT calculations for new problems. And I hope it became clear that it should be much better than DFT plus U, yeah, which is very limited in range. And but DMFT calculations are not a black box calculation because there are some other things that come. So now I think I'm over time. So yeah. So again, there would be a second part with DFT, DMFT, but I think that is maybe then for discussions. If you're interested, I'm very happy to discuss this with you, because it would take a bit more time to go into this. But the strategy is more or less clear. Now you have to define a kind of correlated subspace in your material, which you treat with DMFT, and the remaining part you treat with DFT. So that is a very basic idea behind it. And it's just about how to tackle the different interfacing between these two kind of regions in the Hilbert space to make that work. But it's a kind of a hybrid scheme that is then against that background very, very simple to grasp, I would say, in simple terms. Okay, thank you for your attention.
You have time for questions?
So thank you for this very nice lecture. I'm wondering, in practice, is there a standard good starting point for your G0, or is it based on physical intuition for a specific problem? So for example, if I were to start with something like an atomic Green's function,
right? Yeah.
Do I have to wait too many iteration steps, or is it actually going to be pretty good most of the time?
Yeah, so the standard way is that you start more or less from the dispersions of your lattice. So usually you start from a lattice problem, either from a model sense that you have the hoppings or your Fourier transform dispersion from the hoppings, or you start in the DFT context already from a Cohen-Sham-like Hamiltonian, which describes the non-interacting solution, so to say. And from this you can, since you have this E tilde, so this E tilde would then be the dispersions from your non-interacting problem, for instance. And that is usually a good starting point. So that you just start from your non-interacting dispersions and first define this G0 as a kind of non-interacting Green's function without any sigma. And that is, and then you continue from this. This is a standard point, and this usually converges that quite well. Yeah.
Other questions?
Yes. No, this can be done, of course. I mean, it's in the end, you can also understand, if you like the slave boson, this auxiliary boson scheme as a kind of solver for DMFT, for instance. And if you picture it like this, then it's pretty straightforward. That well, we didn't have time to tackle this, but you can write down in DMFT formalism. Maybe can even jump to that. I have it here somewhere. So in the DMFT formalism, in the end, you have an expression for the total energy, yeah, like this, which is as expected, like a variation of the DFT energy, and then some additions from your interacting part, no? from Green's function that is still written in this Cohen-Sham space, and the through interacting Green's function, your correlated subspace, and the sigma. So then you can use that to compute the total energy from that. Or in a full model sense, you would just go back to this total free energy function that I've written down. Yeah? And if you have defined the Lagrange multiplier knowledge, you would also get a total energy or total free energy from this. So either you can do this via the full strategy of DFT, DMFT, and just insert then the slave boson as an appropriate solver, which describes you the self-energy in a limited term. Or you go back to this model-like calculation when you also have access to the energy or the free energy even by this functional. Yeah? So if you have defined, you have to solve this kind of saddle point solutions when you make the derivative to your degrees of freedom. And once you have defined the Lagrange model, you also get a total energy expression. Well, yeah, it's a good question. But I mean, if the energy is more or less, yeah, so if the energy is carried mainly by the dispersing part, it's usually, well, I didn't really did a big study on the effect of this limited description. So of course, this is a very limited description. If you go to, well, the Hubbard bands are more or less, in some sense, not included in a kind of dynamic way. But if you would go to a more involved slave boson description, you would see that in this total energy function via this Lagrange multipliers, these slave boson amplitudes still appearing, but statically. Yeah? So the occupation of these different slave boson levels, which would here be only the empty side, but like in a multi-orbital model, it would be many more different multiplet occupations. This still appears in the energy function. So you get, so if like a singlet would be occupied more strongly than a triplet state, which in a dynamic fashion would go into the Hubbard bands, but in the slave boson, it only appears as a number, so as an occupation static number. And this occupation number still appears here, which is like here, this only simple R squared, but it still appears statically in the slave boson. It doesn't enter the spectral function, the frequency domain, but it enters statically the free energy function. And therewith, we still have a differentiation of different occupations, so to say, of your Hubbard bands, but not a full frequency dependence. That's true. So there's still something there, but in a static limit, I would say.
Are there any other questions? Or if not, then let's thank Frank for a very nice tutorial.